Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be discussing Reynolds number. This is a continuation of our discussion of fluid dynamics and fluids in general. What Reynolds number is here for is in some ways to give us I guess you could say, indicator of whether or not flow will be laminar or turbulent. So we can begin by recalling that, among other things, fluid flow can be either laminar, which is like streamlined and smooth flow, or it can be turbulent. And turbulent basically means not streamlined, not smooth. Layers mix is one way of saying. So layers mixing would be a type of turbulence, adding a lot of angular rotation within the flow. Beyond that, we can also recall that some fluids are viscous. So what does viscosity do? It's kind of friction between layers. And viscosity as friction between layers means that as layers pass by each other, there's some resistance to that flow between the layers. And if there's sufficient enough resistance and in sufficient enough of a manner, that can introduce turbulence that otherwise wouldn't have been present. And this dragging between layers can cause there to be turbulence. Reynolds number just indicates the onset of turbulence. Now there's several ways of looking at that. One method for looking at it is that you can look at flow rates through a tube, for example. Another is that you can look at drag on or around an object, and that actually represents a modified Reynolds number. So there's not only a Reynolds number, but also a modified Reynolds number. And what the modified Reynolds number looks like is that instead of having the fluid flowing through a tube or pipe or whatever, instead you have the fluid flowing around an object. Okay? And so in the case of flowing through a tube, it's easiest to measure like a flow rate. In the case of flowing around an object, it's easier to maybe measure the drag of the fluid on the object. And so in the case of flow through a tube, we'll start there. So flow through, let's say, a tube with circular cross-section. What you're basically looking at is what is the flow rate. And that flow rate basically should be Q defined as delta V over delta T. And that should look like the cross-section area times the basically the speed of the fluid. But of course this ends up being an average speed. So the other way of looking at it is through Poiseuille's theorem. And so Q should be the pressure difference between ends of this tube or pipe or whatever divided by the resistance to flow. And of course for a circular cross-section that gives us the pressure difference times pi times the radius to the 4th power of the tube divided by 8 times the viscosity times the length of the tube. And so this right here, this equation is valid for laminar flow. Okay, and so one measurement of the laminar flow is if you can measure these other quantities, viscosity, length of tube, radius of the tube, or inner radius, and pressure difference, that as the flow is more laminar, this flow rate will tend to agree more with this equation. And so you'll start to deviate from this equation somewhat as the turbulence starts to increase. And so Reynolds number imposes ranges. Below this value, you pretty much are in agreement with this equation. At some value, some intermediate values, you start deviating from this equation, and then at some point in time, you end up with total turbulence, and the result is that thereafter, increasing pressure further or pressure difference further should increase flow rate again. And so you end up with a plot, let's say, that has flow rate on one axis and pressure difference on the other. And basically that plot looks linear for some set of data, and then all of a sudden you end up with a little bit of a drop because turbulence is onsetting, and then it ends up more or less increasing at some value. And so in this region right here, this is where turbulence is onsetting, and this is totally turbulent. So turbulent, laminar, and then this would be like a transition region. So that's one way of looking at measuring turbulence. Okay, for flow around an object, what you end up having is drag. And so your drag force should look like negative B times V. For Stokes' law drag force, we could say the force for Stokes' law is 6 times pi times the viscosity times the radius times the speed. So this is your non-turbulent drag. This is non-turbulent. And essentially what that means is that we expect, as turbulence increases, for the drag force to deviate from this equation. For example, instead of being proportional to the relative speed of the fluid around the object, maybe it becomes proportional to the speed squared, as in the drag that you get from air resistance. All right. So again, you would expect there to be some intermediate region where it's transitioning from v to the first power to, say, v to the second power. So where do these Reynolds number and modified Reynolds number come in? Well, Reynolds number is often represented as N sub r, and it's simply given by the following equation. The Reynolds number is twice the density of the fluid times the speed of the fluid through the tube times the radius of the tube divided by the viscosity of the fluid. So remember, this is fluid flowing in circular tube, or flowing through tube or pipe or vessel with circular cross-section of radius r. And so your Reynolds number is just calculated by this combination. Well, then we look and say, all right, what are the possible values for it? Well, you can either have a Reynolds number less than 2000. This is generally laminar. So this is more or less going to behave like the Poiseuille's principle equation, where if I increase the pressure linearly, then my flow rate linearly increases with it. This is my transition values, and this right here is generally turbulent. And even if it's turbulent, once you're in the generally turbulent regime, increasing the pressure difference does increase the volume flow rate. It may even increase it linearly for quite a while, but it does so at a different slope, a smaller slope in fact, than in our generally laminar case. Okay. Similarly, there's the modified Reynolds number. So the modified Reynolds number, which is given by n prime of r, that represents the modified Reynolds number, not a derivative for those who have seen calculus. This is just to distinguish it from the Reynolds number, is the density of the fluid times the speed between the fluid and the object times a length, a characteristic length for the object divided by the viscosity. So again, this is what's called characteristic length, and the characteristic length depends upon what kind of object you have. If it is a sphere, then the characteristic length is actually going to be like the diameter of the sphere. V, again, is the speed relative, or the relative velocity of fluid with respect to object. So this means that this is valid if you have a fluid which is moving around a stationary object, like a boulder. It's also valid for an object which is moving through a more or less stationary fluid. So like if I am sitting at the lake and I drop a rock or a fishing bob or something into the water, then this equation is still valid. Okay, now the ranges for this guy are a little bit different. If the modified Reynolds number is less than 10, we basically have laminar flow. If we have somewhere between 10 and a million, it's kind of transitioning to turbulence. And then if you have greater than a million, this is generally turbulent. And transitioning to turbulent, going to turbulent, basically what that means is, in some sense, how much turbulence do you have surrounding the object? And does it totally surround the object, or does it just occur, let's say, in the wake of the object or in front of the object, etc.? So essentially, the larger this number is, it's not just that you get more turbulence, it's that the turbulence more completely surrounds your object. All right? So that is the Reynolds number, and that is the modified Reynolds number. All right, as an example, we might ask how fast water can flow through a tube of radius 1.2 centimeters if it is to remain generally laminar in flow. We can look up the viscosity of water at 20 degrees C, and we can look up the density as well. So the density, of course, is about 1,000 kilograms per cubic meter. The viscosity, on the other hand, is about 1.002 millipascal/seconds. Now, what we're solving for here is the number, the Reynolds number, has to be less than about 2,000. And we know that the Reynolds number is given by 2 rho VR over eta. So this means speed should be eta times Reynolds number divided by 2 times density radius. Plugging in numbers and throwing into our calculator, we get about 0.0835 meters per second. So about 8.3 centimeters per second. That's all. Thanks.